Hello, everyone. Good afternoon in Shanghai and good morning in Switzerland. Welcome to the first Café event of 2022. Our topic today is assistive technology for individuals with visual impairment. My name is Kathy Lee. I'm the Art Science Junior Project Manager at SwissNex in China. Before we start, I will give a short introduction of our organization as well as this lecture series. SwissNex in China is the science consulate of Switzerland in China. As part of the SwissNex Global Network, we connect Switzerland, China, and the world in science, research, education, and innovation. Our mission is to support the outreach and active engagement of our partners in the international exchange of knowledge, ideas, and talent. The 6 main SwissNex locations are established in some of the world's most innovative regions: Boston, Brazil, China, India, Japan, and San Francisco. SwissNex is an initiative of the State Secretariat for Education, Research, and Innovation of Switzerland, and is part of the Swiss Confederation's network abroad, managed by the Federal Department of Foreign Affairs. The event today is part of our Café lectures initiated in 2019. We try to present a Swiss spotlight scientists, startups, artists, and designers in the series and connect them with the local network. This year, we will focus on the theme of social innovation, and today we will look at the topic of assistive technology. We have invited 3 speakers in the field. Professor Dr. Alireza Darvishy, head of ICT Accessibility Lab at Zurich University of Applied Sciences School of Engineering. Arthur Gassner, software engineer at the Swiss startup Biped.ai. And Dr. Yang Jiao, assistant professor at the Future Laboratory at Tsinghua University. They will share with us their projects and how they harness modern technology to empower people with visual impairment in their lives, study, and career. We will have the Q&A session at the end of the event, but you may type in your questions in the Q&A box throughout the lectures. Now, without further ado, let's welcome our first speaker, Professor Dr. Derbyshire from Zurich University of Applied Sciences. Professor Darvishy has been committed to accessibility for over 20 years. He is active in both the private and academic sectors, and he is recipient of the 2016 UNESCO Award for Digital Empowerment of People with Disabilities. He will introduce his recently funded project, Accessible Scientific PDFs for All. Professor Darvishy, the floor is yours.
So you hear me now?
Yes, we can hear you.
Okay.
Although we can't see you yet.
Okay. So now you see me as well, right?
Yes.
Okay.
Yes.
Thank you for the introduction. That's an honor for me to be here and give a short interview about our project, Accessible Scientific PDFs for All. So the topic here is about assistive technologies for people with visual impairment. I have the role of being a scientist and also being as a person with a visual impairment, severe visual impairment. Maybe I share my screen. Okay, you see my screen now?
I can see that you have started screen. Yes, we can see your screen.
Okay.
Inbox dash file symbols underlined. PowerPoint slideshow dash cafe on. Slide. Shift F1.
So that's my presentation,
Slide.
maybe project goal. The project goal is to use AI technologies to research and development of AI-based technologies to create accessible PDF documents. So what is an accessible PDF? We will talk about it later. So especially we are interested in using deep learning, which was one of the disciplines of AI, to leverage these technologies to create accessible PDF documents for people with
Slide 3 dash problem statement. Decorative.
visual impairment.
Slide.
So that is a Swiss national, there's a program, funded program, is a joint program in Switzerland from Swiss National Foundation and Agency for Innovation, InnoSwiss, which is called Bridge Discovery Project, the Bridge Discovery Funding program. And that is given to experienced researchers who would like to have both aspects of fundamental research and also applied research. So I was one of the few appliers who got the funding for this project.
Slide 3 - problem statement. Decorative.
So what's about? There are more than 250 million people worldwide living with a visual impairment. In Europe, we have about 30 million people having a visual impairment, including blindness or different kind of visual impairment. And also there is a legislation in Switzerland, also in Europe from the European Union, so-called European Accessibility Act. And this law says that PDF documents should be also accessible for people with visual impairment. So what does it mean? In order to understand it, I use the term assistive technologies, especially in our context, digital assistive technologies. Simply described, these are soft and hardware elements helping people with visual impairment to overcome or eliminate their barriers in their daily life. A special assistive technologies which are used very often by people with visual impairment is a screen reader. Screen reader is a piece of software who reads the information aloud to the visually impaired person. So by myself, I have a severe visual impairment. It means I'm not able to read the information on the screen without having a screen reader. This information can be also presented on a so-called Braille display. There's also possible, there's another component of assistive technology which is used by people with visual impairment. So what's the accessible PDF document? In order to show that, I have to show you what is in the screen reader. And there are different kinds of screen readers. A popular one is ZHAW screen reader. There are also open source screen readers such as non-NDVA, non-visual display application. And there are other brands as well. So
meeting controls. Inbox -- samples underline. Café underline. JAWS professional. JAWS
so you hear also the sound, right? You hear the sound of my screen reader. Is that correct?
Yes, we can. Yep.
Okay, that's a JAWS screen reader. That's a commercial product. And I use this software to read the information on the screen. So
PowerPoint slideshow - meeting controls. Inbox -- JAWS samples underline.
I use
Date modified 1/1. 2 underline document.pdf. Check enter.
Use a
Items view multi.
PDF document. Unfortunately, this document is in German, but it's from ETA.
Items view multi select list box. 2 underline document.pdf. Check 1 under JAWS professional. PowerPoint slideshow meeting controls. Inbox -- Café underline underline 2 underline document.pdf - Adobe Acrobat Pro DC left parent 30. Blank. Samples 2 underline document.pdf - Adobe Acrobat. Samples underline. 2 underline document.pdf. Check enter. Reading order : combo box. Enter. 2 underline document.pdf.
So this document is in
Tool for continuing education.
back.
Period. Diploma for
I
funds.
can
Diploma.
read
Period.
aloud the information line by line.
Administrative Fragen. Fragen Zersley administer. Signed dice and matriculation. Mithers and lessons. There's Waymo Gerlich Sweden. Diet. Left. Right. Word. Date. And my detail. Dollar days.
So you might ask me, is this document accessible? I say partially, because I can only read line by line, word by word, or letter by letter. But imagine if the document is long, I have perhaps many days to read one document. So if you have a normal vision, you see visually the structure of the document. You see the headings because they are bold, normally bold, or when there's a table, you see it immediately, and you can focus your vision toward the section which you're interested in. So by having such a document, I can only read the document, but still this document is not fully accessible. In order to make it accessible, I can show you another example.
Samples underline. 3 underline document. Enter. Download Studios document. Page has 11. Mouse.
So this document is somehow accessible. How can you recognize that? As I said, if you have a normal vision, normally you can navigate through the document. You can identify quickly the headings, the tables, the links, and other kind of information. In order to provide the same experience for a screen reader user, it is a technology available. So you can mark the different section of the document. You can mark the headings. You can mark the tables. You can mark the links. You can provide alternative text for an image because the screen reader user is not able to recognize an image if you don't provide an alternative text. So if you mark all this information, this document then is accessible to a visually impaired person. How do you do that? There are different options. If you are creating a PDF document from a Word or PowerPoint, there are some infrastructure, some possibilities to do it. But if you use, for instance, you have a PDF and you want to make it accessible, there is a technology available from Adobe called tagged PDF. So these different marks that you set, heading, table, they are tags actually. You have also these tags in HTML. If you have a web page, if you have a Word document, for instance, you can use different style sheets such as heading 1, heading 2, heading 3. Is also similar to this technology. That's also, there are special tags that you set in your document. So how do you do this? How do you set, if you receive a PDF document, you want to make it accessible? So there are different options. You buy a commercial software such as Adobe Professional, and you have to have knowledge how to make a PDF accessible. It needs a special know-how.
Samples underline. JAWS Professional. PowerPoint slideshow Café.
So in order to make it easier, my team developed a software called PAVE. PAVE stands for PDF Accessibility Validation Engine. That's a free software. So the scenario is like this. You have a PDF document which is not accessible. You can upload the document to this web page. The software analyzes your PDF document and fix some accessibility issues automatically, but some others should be done through interaction with the user. For instance, if you want to define alternative text for an image, so user should tell you what's the best option. Though using AI, you can also somehow create also alternative text, though they are not so perfect. So this software allows you to create accessible PDF documents. But what are the disadvantages? It's very time consuming. It's to make a PDF accessible, even using PAVE, you need a lot of time. Though you don't need a special knowledge, you can easily learn this knowledge as we compare to the solution which I described using Adobe Professional. So you don't need a special knowledge. You can also, we have video tutorial, you can watch them and quickly create a PDF document, but you can only use it for small document up to 5 pages. It's very time consuming, and also it doesn't solve many problems. If you have scientific PDFs have mathematical formula in them. They have graphs, they have graphics, they have tables, and this software doesn't allow to do that. And as I said, this process is very time consuming. In order to tackle these issues, especially for scientific PDF documents, we propose this project.
Slide.
You see here a pipeline, a software pipeline. It's very complicated, so I quickly describe it. So you have on the left side, you have a scientific PDF document which is not accessible. So you have here a software pipeline from left to right, and it uses AI, deep learning, to, for instance, identify the structure. We say zone detection and classification. It means that in a PDF, in a scientific PDF document, you have mathematical formulas, you have graphics, you have tables. So the task of the AI is also automatically identify these parts. And also we think that the software maybe cannot automate everything, but we try to do a kind of semi-automation in this process. That's why after each step, maybe it needs some human intervention. Maybe there are some errors that only a human being can correct them. So when you move to the right, so we have different components to identify the mathematical formula, graphics, tables, and so on, and also to interpret them. A special focus lies on identifying and identification and interpretation of mathematical formulas, because they're very important for scientific documents. So in order to do that, you have to recognize symbol, you have to find out the relationship between the symbols, you have to understand, you have to find out the semantic of the formula. And when you go through all these steps, hopefully you have an accessible scientific PDF at the end. And also we assume developing different additional software, so a visually impaired screen reader user can navigate and interact with a mathematical formula. Here,
slide.
Last but not least, this project has different impacts. It has technological impact, social impact, and also economical impact. So in terms of technological impact, we try to automate many steps as it was shown on the previous slide as possible. So we try to make the need for the human intervention to correct the errors from the software in a very minimum way. It has social impact because this project helps scientists with visual impairment, including myself, to access to the huge number of documents, PDF documents, school documents, or university documents, or scientific documents. It has economical aspect because, as I described before, there are legal requirements that the document should be accessible in Europe, and also in the US, we have American with Disability Act or Rehabilitation Act in the US. And also maybe in China, I assume, or in Korea and Japan. So many conference organizers would be very happy to have a very good tool to easily create accessible scientific PDF document. So that's all. Thank you for your attention.
Thank you, Professor Darvishy. Professor Darvishy has mentioned that he have a have a meeting right afterwards. So, and he has also kindly offered that if the audience have any further questions, he will be happy to answer them through email. So at the end of the session, after our Q&A, we will also show you our email address where we can be reached. And now let's welcome our second speaker, Arthur Gassner. Arthur is a software engineer at the Swiss startup company Biped.ai. They are working on a wearable device, which would be the world's first AI co-pilot for visually impaired persons. They have actually just returned from the CES, the Consumer Electronics Show, where they won the first prize of the Swiss startups from Swiss Tech. Okay, so now let's welcome Arthur.
Hi there, can you see me?
Yes, we can.
Yes, wonderful. All right, let me then go to the screen. And can you see my screen as well?
It is, yep, we can see it now.
Yeah, all good. Cool. Nice to meet you. Thank you all for being here. My name is, as was stated, Arthur Gassner. I am a software engineer at Biped.ai. We just came back from CES. And today we will dive into one of the areas of our software pipeline, namely the ground plane detection. All right, so let's dive in. First, a little bit about myself. As stated, Arthur Gassner, software engineer, Biped.ai. I hold a master's degree in robotics from the EPFL, and my main areas of expertise are in machine learning and computer vision. But what is and who is Biped.ai? Biped.ai is a Swiss startup. We're building the first AI copilot for the blind and visually impaired. Our technology is a device that you wear on the shoulders, as seen here. It has 3 3D cameras that capture the environment around the user and then tracks, predicts, and identifies the trajectories of the objects surrounding the user. All of this is done in real time and locally on the device. Then we focus on what matters the most, and we feed back that information to the user through 3D audio to guide them. Now, the thing is, if we're guiding the user, we need to have a way to figure out where is it safe for him or her to walk. We need to have some kind of ground detection algorithm that can tell us, okay, you can go there, but you cannot go there. For the sake of example, here is the data stream from one of the 3D cameras we have. On the left, you have a grayscale image. On the right, you have a depth image. What we want is some kind of algorithm that for each frame will predict the mask of where the user can walk. To do that, we could use deep learning and have some kind of a semantic segmentation algorithm. But the issue is, as I stated, all of the computation is done offline, on the online of the device in real time. And deep learning is usually not, let's say, computationally cheap and power cheap. So we have to find another way to do that. And I will now walk you through how we do it. The way we do it is inspired from my paper called Fast Cylinder and Plane Extraction from Depth Cameras for Visual Audiometry. What we do is we take the depth image and then we divide it up into a grid of superpixels. One superpixel is a square-shaped set of pixels. Now, what we want to identify are the superpixels that correspond to the ground. Usually the ground is flat. So really what we want is to find out which superpixels have data that is laid out in a plane. So planar superpixels. To find those, what we do first is we look at each superpixel and we discard them if either there is too much depth variation in them or if they have too many invalid pixels in them. Once we have done this, we should end up with superpixels that are roughly planar. The thing is, this will also keep the door, for instance, or any flat surface, really. It will keep the ground and the walls and the ceilings and any flat areas that we'll have on the image. So we need to find a way to aggregate those superpixels together and have regions that will be that's the door region, and you have the floor region, and you have the table region, any flat areas. The way we do this is through region growing. We want to merge similar superpixels together so that they form a region. When I say similar, I mean laid out in roughly the same plane. The way it works is you pick one superpixel, and then you compare it to an adjacent superpixel, and you say, okay, are those two superpixels close enough in terms of planarity? Are they laid out on roughly the same plane? And if they are, yes, cool. You can then merge them together and increase the region. If they're not, then you just skip them. What you end up with is a region where all of the superpixels inside of it are roughly similar. They're all roughly on the same plane, and they're bounded by non-similar, by dissimilar superpixels that are not laid out on the same plane. Now, the next question is, how do we compute this similarity between the superpixels? If we want to find out, okay, are they laid out on the same plane? We need a way of doing this. The way we do it is through PCA. PCA will find the directions that explain the highest variance in the data. If we apply it to a 3D point cloud, we can end up with, we can use the least significant component of the PCA as the plane's normal, because that will be where we have the less variation in the data if the points are laid out in a plane. So now we have the normal of each superpixel, and that gives us the power of comparing them, because we can do the dot product of that normal and figure out how close they are on the plane. For the sake of example, let's look at one frame. We've divided that up into superpixels. The first step is discarding all of the superpixels that are non-planar. That's what we end up with. And then what we want to do is region coring. So for each superpixel, we compute the PCA, we extract the normal vector, and then we compare those normal vectors between the adjacent normal vectors. This yields us 3 regions. The green one here is the floor. We know it's the floor because we know what the frame is like, but this is the first region, corresponds to the floor. The second region is some pole that was in front of the camera. And the third region is the wall that was on the outer right. Now, how do we differentiate between those 3 regions to know which one is the ground? Well, what we do is we just say that the bottommost region is the ground, because it's usually where the ground is located. And there we go. We have a ground plane detection algorithm that can detect in a rather robust way where the ground is and where we can walk. The issue with this is it's extremely slow. It's far too slow to be run online and not in real time. So we need to find ways to optimize it. The first thing we do is we profile the code to see if there are bits of it, functions or modules that are used quite often and that make up for a lot of the compute time. And it turns out to be the case. PCA is taking more than half of the compute time. So we want to optimize PCA. The first thing we do is we try to see what is actually computed. When you compute PCA, you take the superpixel, you take all of the pixels within that superpixel, and then you compute for all of those data points, you compute the PCA. We don't actually need all of those data points if they're laid out in roughly the same way. We can subsample randomly those pixels, use less points, and it will hence be less expensive to compute, although it will come at the cost of accuracy. But that's one first step towards a real-time runtime. The next thing is NumPy. Computing the PCA is computing the eigenvalues of the covariance metrics of your points. We use NumPy to do this, and NumPy is this widely used linear algebra library for Python. And one would expect this widely used linear algebra for Python library to be highly optimized and blazingly fast. But the thing is, it also needs to be extremely versatile to cover a lot of edge cases. So if we look at the computation of the covariance metrics, we see that a lot of checks are done every time you call it. Those checks are there to ensure that the data you feed to the function are actually not one of those edge cases. We know that what the data we're feeding it to the function is not those edge cases. So we know we'll always pass those checks, and hence their relevance. So we can just not do them, go straight to the computation, and have on top of the random sampling, we have a 3 times boost. So that's good. We went from 0.2 FPS to 0.6 FPS. It's good, but it's not quite yet enough to run in real time. The next trick is to use Python. What we do first is we identify functions that are very often used, especially in for loops in the Python code. Then we move them to Python. Python is a superset of Python, where you can also write in a C-like syntax, and that enables you to have a faster runtime. Doing this, so first, and here's an example of the search functions. What we do is we select a bunch of functions that are very often called, we move them to Python, we implement them in Python, and overall this gives us a roughly ×20 runtime boost. And there we go. We went from having nothing to having a ground detection algorithm that works, but is not really real time, to one that we can run in real time on the device locally. And there we go. Thank you for listening to this talk. To quickly summarize, to detect the ground, what you do is you divide up the space in superpixels, then you discard all of the superpixels that will not be the ground because they're not planar. And then you compute for each of those superpixels their normal. Then you do region growing and you select the bottommost region as being your ground. To make it faster, you do random subsampling on the PCA, you bypass NumPy checks that you don't actually need, and then you identify and move the frequently called functions to Python. I would like to thank Swissnex in China for inviting me and Biped for this talk, as well as Aman Bansal, who worked on this and whose internal presentation was heavily inspired from for this talk. Thank you. If you have any questions, I'm happy to answer them at the QA session afterwards.
Thank you, Arthur, for your presentation. If anyone have any questions, you are welcome to type in the Q&A box. You can see the button at the bottom of the Zoom window. And at the end, during the Q&A session, we will select them and have our speakers answer them. Okay, now let's welcome Dr. ZHAW. Dr. Yang ZHAW is the assistant professor at the Future Laboratory at Tsinghua University. And he will introduce his work in developing a graphical tactile display, which can dynamically generate Braille and other tactile graphical information. Dr. ZHAW, the floor is yours.
Thanks very much, Kathy, for a kind invitation. And yeah, I think I need to share my screen. So yeah, I see. All right, everything good? Okay. Yeah, so thanks. And I'm Yang ZHAW from Tsinghua University, and it's my pleasure to share our 10 years research work on haptic perception and interaction experience for the visually impaired and the design of a graphical tactile display. And first of all, there are a great number of blind and visually impaired people worldwide and in China. According to China Disabled Persons Federation statistics, there are 70 million visually impaired people in China, but only 40,000 blind and visually impaired students can go to school. This is a number from the Ministry of Education in China. So many visually impaired people cannot get compulsory education due to disability, travel conditions, economic conditions, school capacity, and other reasons. So it has become a rising issue for us. So in this work, we have made a lot of blind friends because we know their lives. So she is one of them. And this is a photo we took in Beijing School for the Blind. Her vision is severely impaired, so she has to move very closely to the computer to catch something. So in fact, most of the visually impaired people, they are very eager to learn more knowledge, and they try to communicate better with the outside world. And these are some more photos from their daily learning. They can, like us, use computer, but just by screen reader and some voice assistant software, and read Braille books. But there's a very limited tool to help the blind learn and understand graphical information. Currently, most of them and the blind school are using like this paper-based tactile graphics. They may deteriorate quickly and they are very bulky and therefore difficult to store and transport. So in contrast, they may need a refreshable tactile screens to display and render graphic information. This concept was raised actually in 1969, a lot of years ago, when a famous TVS system was invented and published in Nature. Up to now, however, lots of the companies and research institutes are still focusing on this topic in order to design a better and more affordable device for the visually impaired. So in this work, we studied the blind user experience of the tactile interaction, the explore multimodal immersive combinations, and then we made the UX-oriented haptic interaction design and implement a low-cost graphic tactile display. So there are some literature reviews of Chinese Braille. They are totally different from Chinese characters and also different from English Braille, because in Chinese Braille, each word are made of an initial and a final, and this phoneme sounds together. So it's actually a pinyin system. So sometimes it is ambiguous, and the reader need to rely on the context to get the meaning. And apart from the Braille word, Chinese Braille also has a notation in music and in mathematics, physics, chemistry, a lot of like this. So actually, these are from the textbooks from the blind school. They learn nearly the same lesson, the same knowledge as normal people. And this is their math test paper. It's all the same as ours, actually. Then we report some researches of tactile sensations and perceptions. Firstly, this is a concept of tactile resolution. So namely 2-point threshold. It is smallest on the fingertip and lips about 2.5 millimeter. So here is how the Braille dot was designed by this. Then we discovered that tactile perception is from the local detail to the overall cognition. So it is much smaller than vision, much slower than vision. And moreover, the bandwidth of touch is much smaller than that of a vision. So in terms of tactile graphics design, we usually divide the graphics by semantic segmentation and deliver the key points to the blind people. And lastly, it is very difficult for them to understand the perspective principle, since they don't have the empirical visual experience like us. So they need to learn how to map physical 3D world to 2D perspective image. And we also invited some blind and sighted participants for an fMRI experiment in Tsinghua Medical School. And we compared them as two groups. So we can see that the primary visual area of the blind people is significantly less than that of the sighted people. But the hand kinesthetic area of the blind people is no greater than that of the sighted people. By doing all above researches, we would like to design a device that can benefit them for Braille and tactile graphics learning. So for example, it can be used in school like an e-book. Also, it is a personal computer for them to social sharing and even internet shopping. And we designed a tactile audio multimodal interface like this. It can display very large ground of graphics like chemistry, like art. And there are some more interface design. And then this is our prototype Braille, a graphic tactile display and a computer for the blind. And yes, some more photos. And this is how we display the graphics by pin matrix. And with this device, we designed a math demo class cooperating with the teachers and students in Beijing School for the Blind. You see here the photos of their classroom and math textbooks. And we picked 2 lessons as shown here. So you see here, this animation simulates the dynamic display. From step to step, the blind students can gradually understand the change of geometrical graphics. You see, so this is what exactly they can touch, like this. And also the same, this lesson is the same thing. And we made 30 blind students as a participant They took part in our demo class. From the experiment, we have made a lot of analysis, and all of the participants were very excited and glad about this new learning experience. It definitely outperformed the current paper-based learning. And the end, I would like to share a very short video to make a more
关于
intuitive
历史、
experience.
地理、艺术、物理和汉字，都是我乐意去阅读的。因为在阅读的过程当中，你会发现离这个世界会越来越近，你自己的内心也会得到更大的一些成长。我们在平时阅读的时候，确实会遇见很多的问题，因为盲文它是通过拼音来显示的，而不是像汉字那么直接。
正在打开百科词条搜索功能，输入激活。
但是像现在呢，我们就可以通过上百科，然后给一些生词呀，来得到一些理解。像我们去博物馆的话是很少的，因为去博物馆我们是无法看见它的展品的样子。
正在打开青花竹石纹玉壶春瓶读图引导功能。
但是通过带着一双全盲的眼睛去到博物馆，好了很多很多。我们基本是衣服的，如果有了就是更规范的版型的话，会更方便上购置衣服的话，会方便很多。像现在呢，这设备是完全把明眼的转换成盲文的，那么对于我们来说是非常感谢清华大学，正是因为接触到了这些设备，所以才让我在学习生活当中变得会便捷一些。
Okay, maybe there are some internet problem because the video is not quite smooth. I'm sorry for that. And lastly, I would like to say that right now, this is still right now a prototype, but we are already about to do a setup and do real production. So we hope that our research can really benefit thousands and millions of visually impaired people, not only in China, but in the world. Thank you very much.
Thank you, Dr. Zhao. And yes, a few viewers in China, there might be a lag of the video, but later we will send out the recording version of the video, and in that one you are more than welcome to check out the video there. That should run more smoothly.
Sure. Thank you.
So great. Without further ado, I think we're going to open up the floor for questions. Actually, I have one here that's directed at Arthur at biped.ai. Thank you for guiding us through the journey of developing a product. It's great to be able to learn more about what it takes to develop a novel device. And our audience is asking which step or what challenge was the most difficult to overcome during your journey?
All right, so hi back. Thank you kindly for the question. Yael, I think it's pronounced correctly. So as I said, Aman is the one who worked on implementing this. One big thing he had was very quickly we had a working prototype, and the challenge was really to make it run in real time. And the profiling, it's one slide in the presentation, so it's seen as if it was super fast. It was not. It took a lot of time to figure out where in the code is the bottleneck and how do we bypass that bottleneck. Like what steps are absolutely essential and cannot be modified. Okay, that's the best we can do. And where can we actually be clever and have good insights to make it faster. But thank you for the question, and I hope my answer answers it.
Arthur, actually, I know that if I'm understanding it correctly, biped, which is the name of the product, it is already in beta test. Is it right?
Yeah, absolutely. I mean, the device, maybe you can see it. It's right behind me on the mannequin. We're still in the prototype phase. We're about to begin the industrialization, and the hope is to, I mean, the goal is launching in middle of 2022.
Mm-hmm. Yeah, and I know that at the CES, I see that you also have several visitors at the venue to test out the device. Is there anything unique that you find during this test?
I mean, we did. So in the US, we took the opportunity to also do other tests outside of CES. We had a bunch of tests that happened straight at the booth during CES that people could try the device and see how they liked it. The feedback is usually that the form factors, I mean, that it's quite good. That you don't feel, it's already quite light, but you don't really feel it because the way it's equilibrated, it feels as if the front is compensating for the back and vice versa. The feedback for the obstacles is quite useful. It gets a bit of time, like within 10 minutes, you can start moving around, and then within an hour, usually, you're able to identify what is where and where is what. But yeah, good feedback. We then had a meeting with Lex Gillette, the world champion of long jump for Paralympic. I don't know if you know about him. He tried the device. He liked it as well. Yeah, this was the feedback from the whole US and CES, and we're quite happy with it.
Yeah, we're also very happy to know that you had a very fruitful run over there. I have a question here for Professor Darvishy, which says, thank you for sharing your work. In addition to tagging their PDFs, are there any other checklist or recommendations you have for researchers who want to make their work more accessible?
Yes, I think raising awareness is the first step, that the people knows. You know, many scientists, they don't know how to make their work accessible. Raising awareness is important, but I mean, there are a lot of also information in the internet. When depends how you create your PDF document. If you create it from Microsoft Word, for instance, there are some accessibility checkers already built in. You know, you can test, you can verify your document in terms of accessibility, and then finally create an accessible PDF document. But our tool, PDF Pave tool, is also a good tool, but as I described, you cannot really use it for long document, and also you cannot make really scientific PDFs accessible, because when they have mathematical formulas, they have graphics, so it needs additional effort. So we hope that the PAVE version 2.0 have all these features and makes the work, the process of creating accessible PDF much easier and faster, as especially for conference organizers or any researchers or anybody who wants to create accessible PDF.
Mm-hmm. Thank you. And I have a question here for Dr. ZHAW. Thank you for the fascinating insights. Will the devices be owned by individuals or rather by institutions?
Yeah, thank you very much.
Yeah, the intended buyers.
Yes, so actually, it is a very interesting question, and this is the challenge we are still facing, because in China, there is a so-called list. In this list, there are all of the assistive tools, assistive device for the visually impaired and the hearing loss people, something like this. And we trying to make our device into that list, and then not only government and some NGOs, some foundation will support the blind and some impaired individuals to have this device from this list, like free of charge, or even a very cheap price, so they can support the majority of the price. So in this case, the individual can very easily we can get that device. And also we try to put this device into like a blind school or museum and library, a lot of the public spaces. So I think for those of people who don't have the device, they can go to their public museums and enjoy this device.
Yeah, thank you. And I think Professor Darvishy, you have also mentioned right now on the market, there are already Braille displays or Braille computers. I'm not sure if for Dr. ZHAW, do you see what is the main difference or the biggest advantage of your device from the current, the current assistive technology devices on the market?
Yes, I meant so-called Braille displays. You can, so the refreshable Braille displays, they call it in technical terms. And you can read the Braille alphabet on it. So the output of the screen reader could be as a speech output, or it could be presented on a Braille display, which is part about maybe 80 letters Braille display are presented on this refreshable displays, and the blind person can read them. But the other work from my colleague presented here is more also, presenting also graphics, the graphics, so you can do, it's not only Braille displays, it's also really shapes and also graphics that you can present on this tactile display. That's, I think, the main difference, as I understand.
Yep. Do you have anything to add, Dr. ZHAW?
Yeah.
I also see, yeah. Sorry, go ahead.
Okay, yeah, and yeah, thank you, Professor Darvishy. I really appreciate your talk, and actually, lots of some students in computer department in our university, they have indeed some also similar researches about yours. They use AI to do a screen reader, and we all know that for some PDF or for some text, and it is very difficult to read by the normal screen reader. So they use deep learning and CNN, some technology, some algorithm to do that. And I think it greatly benefit the people, the blind people, and they can just like us use normal, use computer easily, and they can browse everything they want. Yeah.
Thank you. I have another question here for Arthur about whether biped.ai have plans for making the smart harness accessible in China, for example, on university or school campuses.
Yes, absolutely. I can't give you a time scale, but yes.
We actually also had someone be very interested in the price level, anticipated price levels of the biped device.
So
as well as
we're not quite sure right now in what kind of price exactly what the price would be. We're aiming for a subscription model with like low 100 in terms of monthly subscription. But this is not fully set in stone yet.
Okay, thank you. And yeah, and we also have audience. We have someone here interested to know if the team, if the biped team is still actively looking for beta testers, and if so, what would be the conditions for joining the testing program?
So yes, we are always looking for beta testers. We think this is how we can iterate on product and get the best out of it, so that it truly fits the needs of the users. I can give you a link. You can go on so anyone can go on the biped.ai website, which is biped.ai. and register as a beta tester. The conditions, there are none. It's if you want to test it, we can set up something. You don't have to live near Lausanne. If you do, it's way easier and faster. If you don't, we can arrange. I mean, we've had meetings in the US. Right now, our CEO is in Belgium for some further beta testing and meetings. I will type out the straight URL to the beta testing form on the website. Yes, we're always looking, and there are no strict conditions. If you want to test it, or if you know someone who might want to test it, it's better to get in contact and we can figure something out. And thank you for interest, Marta.
Yeah.
Yeah.
Yes, and we will also be including the a link to the information that you just mentioned in our follow-up email to all of our viewers, so you will be able to check it out. Yeah, and we also have an audience here, Professor He Wei. They're saying they're sponsoring blind schools in China and may support the projects. We are very happy to help you connect with researchers in this field, and later I'll follow up with you through email.
Thank you.
Okay. So I think because we're reaching our time limit of today, and if you still have any more questions, you are welcome to write to us at artscience.china@swissnext.org, and we will forward them to our speakers. And you may also follow our social media channels to receive our latest updates. And I want to give another round of big thank yous to our speakers, Dr. Derbyshire, Arthur, and Dr. ZHAW, and also thanks to my colleagues, Cici and Sherry, who are behind the stage. And last but not least, thank you everyone for staying with us. And I'm looking forward to seeing you again at our next event. Thank you all. Hope you have a good rest of the day.
Thank you, Kathy. Thank you, Alice.
Bye. Thank you.